So the way that things move is by force. You push something, it will move. You pull something, it will move. You put something in its way, it will stop because it's pushing against or you're pulling against. Okay? So a force is defined as a push or a pull, and it's measured in a Newton. A Newton is a very specific unit. It is called that's what a Newton is. And so when I look at these two pieces individually, a kilogram and meters per second squared, what letter represents kilograms? That is a mass. What letter represents it formulaically? M. So M. And what letter represents meters per second squared? Acceleration. So from our unit, we just built a formula for force. A force is a Newton. A Newton is kilograms meters per second squared. So force, actually, we'll write it here. Force is equal to mass times acceleration. The units told us that. So a net force is the sum or the total of all of the forces that are in play. Now, the same piece that we had in kinematics where left, down, east, backwards, behind, were all representative by a negative symbol, and south and north. I said east, I meant west. North, east, up, right, forward. Those are all a positive sign. Our forces also will have signs. So you can have a quote unquote negative force. It just means the force in an opposite direction. And we need to remember this piece about acceleration. What way does acceleration work? Towards the center of a mass. Okay, that's key. All right, so an unbalanced force, this one here, acting on an object will cause the object to accelerate or decelerate. This is the second law. An unbalanced force acting on an object will cause the object to accelerate or decelerate. And so it will experience a change in velocity. Now on your data sheet, what does it look like? We're going to look under the heading dynamics. How is it written? I don't think it's written as force is equal to mass times acceleration. Yeah, acceleration is equal to net force over mass. It's simply rearranged. So don't be panicked when you can't find force is equal to mass times acceleration. It's there. All right? Newton's second law of motion refers to any situation an unbalanced net force causes an object to accelerate. This is key. An object experiences no acceleration and is either moving at a constant speed or is at rest when there is a balanced force. So when you're cruising down the highway at 100 kilometers an hour and your speed isn't changing, there is a balanced force between your engine, between your tires, between the asphalt, between gravity. All of the forces are at play. Now, if you took cruise control off and you took your foot off the accelerator, what would happen to your speed? You would start slowing down, but you did not apply the brakes. So you did not apply an unbalanced force. Why would you start slowing down? Why do you think? Why do you think you would start slowing down? Okay, you don't have enough force to keep moving forward. Remember, force is a push or a pull. So if you don't have enough force going forward, there has to be an opposing force that's slowing you down. What's slowing you down? Just think about the action of what's going on. A hill? Is that what you said? A hill would slow you down because now you're working against gravity. But let's say it's a flat road. Why would something come to a stop? Friction. Your tires and the asphalt have this love-hate relationship. Okay? All right. So, when a net force is exerted in the same direction as an object, the object will speed up. So what we see here, we're going to Bob Ross it. There's our object. We have the velocity, so is moving in this direction, and the overall force is moving in that direction. So here's, if you can imagine a ball rolling across the table and I gave it a big shove in the same direction, that ball is going to speed up. But what happens if we're moving in this direction, we take our foot off the accelerator? Well, now the road is pushing against the tires. We're going to see deceleration. Okay. So Newton's second law of motion, acceleration of an object is proportional. We're going to start using some pretty big words now. Proportional to the net force acting on the object. And so what proportional means is that it is directly related to. If I increase, when I look here and I say that force net is equal to mass times acceleration. If I increase mass, so I go from a 1 to a 2, what's going to happen to my force net? It's going to go up as well, equally. If I increase my acceleration by 4, what would my force net go up by? 4. So force net is proportional to mass. Force net is proportional to acceleration. If I was looking at acceleration is equal to force net over mass, if I increase my mass, what will happen to acceleration? If I go from 1 to a 2, it would be divided by 2, right? If I had 1 over 1 versus 1 over 2, my acceleration is going to decrease by 2 times, by half. So what we say there is acceleration is inversely proportional to mass. Over here, force is proportional, as this little fish symbol, to mass. This is we say inverse because this m is in the denominator, right? And we can show that by -1. And you guys know from math, a -1 means inverse. Okay, let's look down here. So acceleration is equal to force net over mass. If mass is constant, then the acceleration, so if I leave mass as 1 and I double force, what would happen to acceleration? It would be doubled. Then A is proportional to force net. Okay? And this little fish symbol means proportional. So then what we can say, those 3 little dots, that's shorthand for therefore. As acceleration increases, force net increases equally. And we can show that by a graph. Where do we find acceleration in this equation? In an A position, in a X position, or a Y position? Oh, you were so close. Right? Y equals mx plus b. So then force would be my x. As force increases, acceleration will increase. Okay? Because A is proportional to force net. Does that make sense? We're just looking at this conceptually. We're just looking at how things change in relation. Okay, so according to Newton's second law of motion, the mass of an object is proportional to the force net acting on it. So if I write it the way that it's in your data sheet, we know that we can rewrite it so that we have force net is equal to mass times acceleration. And just so you know, conventionally, I will always write it force is equal to mass times acceleration. So if A stays constant, then mass is proportional to force net. Okay, CJ, this is redemption time. In this way that it's written, force net is equal to mass times acceleration. Where would we put force net? So close. Y is equal to mx plus b. So if force net's on the left side of the equation, it's y. Okay? All right. There's another opportunity for you to redeem yourself. Okay. So if I put mass here, as mass increases, force net will increase because mass is proportional to force net. All right, we're going to draw 3 graphs here. Okay, if we were to look at unbalanced forces, if we put distance here, displacement, and time, knowing that we're looking at acceleration, what kind of graph would we see? If we're solving for acceleration, it would be an exponential one. It would be this one. Now, if I was looking at velocity and time, what kind of graph would I be looking at? The sweet nothings he's whispering in your ear might be true. Yeah. Right? Because velocity over time is equal to acceleration. So it would be linear. And then if we look at acceleration versus time, if I have an unbalanced force on my distance, my distance is going to radically increase. So think about it. If I leave in my car and I'm at Adventure Automotive, what's the speed limit at Adventure Automotive? How many? 60. It's 60. It turns to 60 just before you hit the hotel, whatever that's called, the Vegas Motor Inns. Okay? So you're doing 60, you're heading out of town. Sorry, I should be more specific. You're heading out of town. It's 60. Then when you hit the gas co-op, what's the speed limit there? 80. So if I was to accelerate from 60 to 80, my distance that I'm covering is exponentially increasing, right? My velocity is increasing at the same rate that my time is increasing. What do I say about my acceleration in relation to the time? What kind of graph would I have? Oh, no. Listen to my words. If my distance in relation to time exponentially increases when I'm accelerating, right? I'm going to cover more ground in less amount of time. My velocity is increasing at the same rate that my time is increasing, right? Because I'm going from 60 to 80. My acceleration is doing what? It's maintaining itself. It's a constant rate. Your acceleration is a constant rate. I am increasing at, let's say, 5 meters per second squared. That doesn't change from 60 to 80. My velocity changes. It's going to go 60, 62, 64, 70, 78, 80, right? My velocity is changing. My distance is going, 5 meters, 20 meters, 50 meters, 200 meters. Like, it's radically changing. But my rate that I'm accelerating at is constant. Thumbs up, thumbs sideways. This one gives you nothing. It's just telling you that you are accelerating at a constant rate. So if this was marked off at 1, 2, 3, then it would say at 1 second, I'm accelerating at 3 meters per second squared. At 5 seconds, I'm accelerating at 3 meters per second squared. At 25 seconds, I'm accelerating at 3 meters per second squared. The rate at which I'm accelerating is constant. That's what this graph line shows. Okay? Okay. Let's look at some questions. Calculate the magnitude of the net force acting on a 1.5 kilogram toy airplane when traveling at 4 meters per second. So, magnitude means what?
Just value, no direction.
There you go. Just value, no direction. So it's saying here, calculate the net force acting on a 1.5 kilogram toy airplane when traveling at 4 meters per second. So like good physics students, we're going to go, I'm looking for force net. My mass is 1.5 kilograms. My acceleration is, and we don't have acceleration because we're going to go back to the question and we're going to understand this. Calculate the magnitude of the net force acting on a 1.5 kilogram toy airplane when traveling at 4 meters per second. My velocity is constant. Do I have acceleration? No. So force is equal to mass times acceleration, and anything multiplied by 0 is 0 newtons. Okay? The toy airplane's not accelerating. So we didn't even have to do the math. We would just know that velocity was constant, and so I could just say 0 net force. There's no unbalanced force there. Says, the second question says, calculate the magnitude of the net force acting on a 1.4 kilogram toy airplane when accelerating at 4 meters per second squared. So good physics students would write this. I'm looking for my force net. My mass is 1.5 kilograms. My acceleration is 4.0 meters per second squared. And to find force net, anytime you're looking for force gravity, force normal, force friction, well, force friction's a little exception, but force is equal to mass times acceleration. That's your base formula. So, CJ, you'll calculate it and Daniel will fact check it. Hmm? 6. Okay. When I look at the question, I have 2 significant digits here and 3 significant digits here. So what's my answer going to have? 2. And my unit is, if I look here, kilograms, meters per second squared, which we know to be 6.0 newtons. Now, if you want to write kilograms, meters per second squared, you can, but you absolutely need to know that a newton is kilograms, meters per second squared, because we work with other kilograms, meters per seconds, and we call that something else. Okay? Yes, we do. Okay. And magnitude required what, CJ? No direction. There you go. Okay. A 22 kilogram object decelerates uniformly and goes from 2.5 meters per second west to a stop in 8.7 seconds. What is the net force acting on the car during this acceleration? So what's the first thing we have to do, Paulina? Yeah, we have to write down all of our known information. So Kyle, give me a piece of known information. Okay, what is that? Cameron, another piece of information? Aiden, another piece of information? Which is what? Another piece of information, Princess? We're looking for acceleration. We're looking for net force. Okay, Joyce. There's another piece of information in this question. Oh. Daniel, do you know what it is? Vf is equal to 0 meters per second. That means that Kyle's velocity is initial velocity. It goes from 2.5 to a stop. It goes from your initial velocity to your final velocity. And you have to be able to decode these things. To a stop, at rest, all those pieces of information tell you something. So it's not just the numbers in the question, it's all of the words in the question. Okay. What about acceleration? We're going to get there. How do we solve for force net, CJ? What's the formula? Okay, I'm looking for this. I have mass. Do I have acceleration in my list of goodies? Nope. I need to actually calculate out acceleration. So now you're going to go to your data sheet, and knowing I have VF, VI, and T, can I solve for A? How, Kyle? Divided by time. That's how you solve for it. On your data sheet, it might be written like this, right? Change in velocity is always VF minus VI. Okay, so then I'm going to take this, and I'm going to go 0 minus 2.5 meters per second divided by 8.7 seconds. Paulina is going to calculate, and Cameron is going to fact check. Yeah, and there's a whole bunch of other decimals, right? It carries on. Now that I have this A, I can now go back to that formula and solve for it. So force net is equal to mass times acceleration. I'm going to go 22 kilograms multiplied by, and you're going to keep all of your decimals. So Aiden, you're going to calculate it, and Joyce is going to fact check. What did you get? 0, 0. I got negative 6.3218. Who said that? You did? 3218 in other decimals. Kilograms, meters per second squared. Okay. Now, we've solved for force net, but we're not done. We have to put it in proper notation. So how many significant digits can I have, Princess? 2. 1, 2. So negative 6.3 kilograms meters per second squared is a Newton. This is technically the end of the question. There is a better way to write this answer, though. What does the negative sign say? Nope, it doesn't. What does the question say? It says that the toy is, or the object is moving from 2.5 meters per second west to a stop. So the force acting on that object to stop it is moving in which direction? East. It's opposite. Okay? Because things only move when there is a force applied. If things are stopping, it's because there's a force against it. Let's look at the next one. It's a bit of a doozy. Canada's motor torpedo boats patrolled the English Channel during World War II. When the engines of a motor torpedo boat exerted a net force of 340 kilonewtons on a MTB with a mass of 5.5 times 10 to the 4 kilograms, the boat could accelerate from rest to 50 meters per second. What is the distance the boat would travel as it reached 50 meters per second? Well, let's start pulling out pieces of information. CJ, give me one piece of information. Kilonewtons. Yeah, you're on the right track. Daniel? Because it's going from rest to something. Paulina? Kyle? And anything else, Cameron? Anything that we're looking for? We're looking for the distance. Okay. I have VF, VI, and I'm looking for distance. What formula using VF and VI and distance could I use? Remember there was like 5 or 6 formulas? Okay, say that again. Do we have time on our list? No. We have VF, VI, and D. D is what we're looking for. right? We have VF, we have VI, we're looking for D. Do we have A on our list? No, but we can solve for A. Knowing on our list here, we have F net and mass. How would we find A? Oops, let's write the word up. Divided by mass. So let's solve for A. Now, there's something special about this 340 kilonewtons. It's got the word kilo in it, not newtons, kilo. And force is a measurement of newtons. So how do we go from 340 kilonewtons to a newton? I want a newton, and I have a kilonewton. In 1 kilonewton, how many newtons do you think there are? 1,000. Okay? Always make sure you're in the right unit. A kilonewton is not a newton. All right. I'm going to get Daniel to come up with the answer for what's on the screen, and I'm going to get Paulina to fact check it. Six what? What'd you get, Paulina? You say 6.1? Is that what you got, Daniel? You're out by a factor of 10, I think. Yeah. Okay. Now that I have acceleration, I can go back and I can solve for my distance. So what we know about this formula, I wish I wouldn't have written that so big. VF squared is equal to VI squared plus 2AD. What is VI? 0. Anything 0 is just going to not be a part of our problem. So VF squared is equal to 2AD. If I wanted to solve for D, I'm going to end up with VF squared over 2A. So I'm going to take 50, square it, and I'm going to divide it by 2 times my 6.18, repeating. Kyle calculate and Cameron will fact check. Oops. Is that what you were saying? Did you square your 50? Yep. Okay. When we go back to the question, how many significant digits are we looking at? Joyce. 2. Is 20 the same as 202? Nope. So what do I have to do? Aiden, how do I represent 202 with only 2 significant digits? Yep, scientific notation. What would it be? How do I represent 100 in scientific notation? What power? 2. 2.0 times 10 to the power of 2 meters. Okay, CJ, this is your question. What is distance? Is it scalar or vector? Scalar, which means what? I don't need a... Perfect.